And I suggested a talk on the history of stochastic filtering, and I'll try to make the point why there's some connection that can be people attending both programs might be interested in that. There isn't a very strong connection, but on the other hand, this is an area which we started in the 40s, and it had a very interesting history. And I guess every area, you can say that about every area that you work for a number of years. You begin to get accustomed with the people working in the area, and you begin to like what people have been doing, and you learn about how they got to do what they did. This is what happened to me. I have been working in this area for over 2 decades now, and obviously in this period I've been talking to some of the greats and not so greats in this area. So I got some sort of image of how the subject came about. I put all of this into a talk. I should say that somehow. So this is a talk that I've given already. There was a meeting in Sheffield last month, which celebrated 50 years since the inception of the Journal of Applied Probability, and so I given this talk there. There was an addendum to this talk at that meeting, which I'm not going to mention it now. So there are some things that I need to say beforehand. I'm not a historian. So that means that it may be that some of the things that I'm saying here are hearsay, and it may be they are incorrect. If you feel that there's something which is incorrect, or is you want to contribute to what I've said, do tell me. I have written a book on the subject, and I have included some stuff, some historical account, some short historical account in the book. Let me tell you this: that as soon as the book appeared, 99 out of 100 of the emails that I received were comments on the 2 pages of the historical account. Yes, people are interested, and we had a meeting earlier today where it does seem that mathematicians are very keen on sort of making sure that their contribution is seen, and maybe we are not the only ones. Anyway, so what I am aware that this is a 1-hour talk. I'm not sure if I'm going to get to the end of this, but if I don't, I will speed up towards the end. So this historical account has 5 parts. It's mostly concentrated on the early years. You'll see that when I go to the last part, to modern developments, I don't cover a lot, not because there aren't a lot of modern developments, there are a lot of modern developments, but as with wine, it takes time to see which of these modern developments are actually important in the long run and which are not. Whether if you look at sort of the first 20 to 30 years of the topic, it's clear by now what was important and what was a dead end, and there were dead ends. So I'll start by explaining briefly what the stochastic filtering problem is, and then I will cover 3 parts. The first one will be the beginnings, say something about the work of Kolmogorov and Wiener, and then I will talk about the famous Kalman-Lucy filter. This is the linear filter, and then I'll go on to talk about the general case, general nonlinear filtering case, where this is work that which covers a period of time that started from sort of the end of the 50s and went well into the 70s. And then I will go on, as I said, depending on how much time do I have, I will talk about modern developments. So what is stochastic filtering? This is mostly for people that attend the workshop on PDEs. This is well known for the people that attend the program on PDEs. This is well known for people that attend the program on Monte Carlo methods. So basically, you have two processes. You have a signal process, and this signal process is a model for a dynamical system. Choose your favorite dynamical system: a car, sort of a satellite in the skies, anything that sort of moves around. And the model is random, so we are assuming that the trajectory of this dynamical system is random. There's random perturbations to this dynamical system, and the position of the dynamical system, in particular this process X, is not available to us. But what is available to us is some additional, some associated process Y, which we will call obviously the observation process, and this process is a function of the signal process and some noise, some measurement noise. So if you have in mind this idea of having a satellite in the sky, you have radars down on Earth that sort of try to measure to find out where the satellite is. So that's your function of the position of the satellite. What the radar gives you, it gives you a function of the position of the satellite, which is sort of perturbed by your measurement noise. And so what you want to compute, you want to find out where the satellite is. You want to find out where the signal is given your data. And so in mathematical terms, you want to find out the distribution of the signal given the entire data. So everything is embodied into a probability measure pi t, which gives you the conditional distribution of the signal given the observation process. So the main object of stochastic filtering is to get to this probability measure pi t, which is a random probability measure. Is random because it depends on the observation data. Of course, if you fix the observation data, if you say that's my observation data, then this pi t is determined. But if you think of this as coming from a sort of random source, this pi t is a random probability measure. So that's the stochastic filtering problem. There are two associated problems: the prediction problem and the smoothing problem. I won't go into this. They are very closely related to this, but I don't want to go into this. Stochastic filtering is an area that has a lot of applications, and people that are coming from different areas call stochastic filtering in different ways. So if you haven't heard the term stochastic filtering, it may be that you have heard other terms that are more or less synonymous with stochastic filtering. If not, they are very closely related to stochastic filtering. So if you're working in statistics, you may have heard of Bayesian inference, or if you work in meteorology, you may have heard of the term data assimilation, or in engineering, uncertainty quantifications. All of these are topics or subjects which are very closely related to stochastic filtering. The aim of all of this is to try to find out to try and estimate some unknown process or parameter and so on. If you have questions, do ask me. The audience is very small, so it's going to be very easy to answer your questions, or can talk after that. So I have a picture. I have Jose here, who's from Imperial, but at Imperial, when you join Imperial, they make you go through some training courses. And if you go to one of these training courses, what they do, they say you have to do a presentation, and if your presentation doesn't have pictures, then you fail. You don't really fail, but they criticize you a lot. So I learned my lesson, I failed, and now I put pictures to try to give examples or illustrate the ideas in my talk. So what I have in here is exactly what I said on the previous page, but in a diagram. So you think about your trajectory of your satellite in here. It's a random trajectory that runs in sort of say 3 dimensions, so 6 dimensions if you take the velocity of the satellite into account. And so you observe this. So your observation process takes values in a different space, depending on how many radar stations you have and what the radar station observed. So what you do, you have a measure, or you have a function of the signal to which you add noise. That's when you take this into sort of direct transposition from the signal to the observation. And it turns out that if you work in continuous time, in order to be able to apply the usual stochastic calculus tools, what you need to do, you need to take these observations and integrate it, and you work with the integral version of the observation. So your observation has this form, which is the integral of this function h, which is called the sensor function of the signal, to which you add the noise, and this noise normally is modeled by Brownian motion. So that's the model. So what you want to do, you want to get to the distribution of the signal given the observation. So the way in which I try to illustrate that is you think of a blob of mass that moves with you. So you're no longer able to sort of get to the signal pointwise. What you can do, you can get to some sort of to a probability measure, which somehow the position of the signal is in the support of this probability measure. Now, in general, this probability measure doesn't have compact support, so this is a bit misleading. It usually sort of has a support that is the entire state space, but just for illustrative purposes, you can think of this blob moving in space. And people that are attending the program on Monte Carlo methods, they are looking for ways for Monte Carlo methods to approximate this blob. Okay, people that are attending the PDE program would be interested to find out what is the equation satisfied by this blob, and it turns out that it's a very nice equation. It's a generalization of the heat equation to which you add multiplicative noise. So from the point of view of the PDE point of view, what you're interested in, to compute or approximate or estimate or study the solution of a parabolic PDE which is perturbed by multiplicative noise. So I'm going to come back to this and I'm going to show you the equation later on. So that's the picture. So now let me just start with the historical account. And the first steps, there were work, Bayesian inference is if you think of Bayesian inference, it's a long subject, or it was subject to a long history. But the first people that began to talk about actually doing filtering, actually looking at signals that are sort of estimated, they want to estimate them, are this. So in the Soviet Union, this was in the 40s. The papers appeared in after the war, but the work was done before and during the war. So in the Soviet Union, it was really Kolmogorov and Crisan. I haven't been able to find out. I mean, Kolmogorov in the Soviet Union at the time, he was the closest thing you can think of God in the academic world, and Crisan was his collaborator in this area. And from the paper you can see that, so the paper is written by Crisan, but he keeps mentioning in the very title he mentioned that this is an investigation of Kolmogorov. So they both of them are attributed sort of filtering on discrete time started to be developed by the two of them. On the other side of the Atlantic, it was Wiener that started the filtering problem. I'm going to come back to Wiener right now. The paper, he wrote a book on this subject, and the book only appeared in 1949. So this was in continuous time, but his work was really done during the war, and I'll come back to this, and I'm going to tell you what were the connection and the relation between Wiener and Kolmogorov. So I'm going to concentrate mostly on the continuous time filtering. So I'll speak about the Wiener filter in some detail. So the Wiener filter consists in the following: you have your signal here, and the overriding assumption that you impose on the signal is that it is a stationary process. So both Kolmogorov and Wiener, they work with stationary signals, and your observation is really the signal plus noise. The measurement noise is independent of the signal and has certain properties. And so what you want to do, you want to estimate the signal. So they didn't really get into this idea that you want the entire distribution of the signal. They just said we want a pointwise estimation of the signal. But the estimation of the signal had to satisfy these three properties. And once Wiener set them up in stones, these were the overriding properties. From that time onwards, they remain the properties that every filter had to satisfy. So the properties are causality. You want your estimation to depend on all your data up to the current time. Optimality, you want to minimize some measure, and the standard measure that some measure. So the way in which you measure the error is to take the difference between the actual position, there's a T missing there, the actual position of the signal and your estimation. These are random quantities, and look at the mean square error to minimize that. So in other words, this is the conditional mean of the signal given the observation, and you want this thing to be online, and that simply means that once you compute your estimate at the current time, the next time when you do it, what you need to do, you need to take this estimate and then just use the additional observation to get a new estimate. So you should not be trying to go back to the beginning. Yeah.
So this book, the 1949 book, was the yellow one, right?
No.
No, that's a different one.
I'll show you in a minute.
Okay.
It's okay. So.
Did he not do non-causal frequency domain estimators and things like that?
In the book, but not originally. So
right.
So Simon is mentioning this. Some light relief here. He did a lot of this work. So it turns out that the estimation looks like this. So your mean square, your estimator is sort of an integral of the observation data with a well-chosen kernel in there called the transition function. And he did this. He studied this during the war, and this was initially in the 40s, in the early 40s. It was in a classified report, and this is so what you see here. Is not very clear, but it's actually a copy of that report. So it's available online if you want to buy it. I didn't dare ask how much it is, but if you go online and type in yellow parrot, this will come up. And if you look at it, it has an inscription there saying declassified. So it is one of the original. It is part of the Wiener original work. So it's available, and it was very hard going. I mean, the engineers apparently hated it, and they called it the yellow perrier because it was very hard to read it. So it didn't do, but they were using it, but it didn't do a lot of. He didn't get a lot of friends because of that. To come back to this,
is this transfer function the same as the sensor function?
No, they are completely different things, and I'm sorry I use the same notation, but they are completely different things. So the question is whether Wiener and Kolmogorov knew of each other's work. It's clear that Kolmogorov published first. It was not clear when did Wiener come up with this work. If you read his autobiography, he says in his autobiography that certain people that he was talking to kept mentioning, you should look at Kolmogorov's work because he has done something which is similar, if not the same thing. And he refused or postponed doing that until somewhere, I think it was in the winter of 41, there was a winter school where somebody put in front of him Wiener's paper or some of Wiener's work. And then he says in the autobiography that from that point onwards, he was aware.
So who did it? Kolmogorov?
Wiener, sorry, Wiener.
Yeah.
So I'm talking about Wiener. Wiener became aware. Wiener became aware of Kolmogorov's work. Now Wiener of Kolmogorov was very sort of great guy. He invited Wiener to visit him. So apparently they visited each other once or twice. But the meetings between the two of them didn't go well. So I know for a fact, I mean, Shiryaev, which was sort of Kolmogorov's favorite student, told me that once Kolmogorov invited him to his dacha and said, why don't you come to visit me tomorrow at 6 o'clock? And Wiener turned up at 6 o'clock in the morning. No, I mean, obviously, Kolmogorov did not expect him at 6 o'clock in the morning. He expected him at 6 o'clock in the afternoon. Shiryaev didn't know what happened with that meeting, but in a subsequent visit, when Wiener said, "I'm going to come to visit you," Kolmogorov made a point of taking Shiryaev and some other people on a long boat on one of the big rivers in Russia to ensure that he's not available. So it didn't go well, and the relations between the two of them apparently were not great. Wiener doesn't say anything about this.
Sorry, was this post-war or during the war?
Post-war, yeah, of course, post-war, yeah. So the next step after that was the linear filters, and indeed it's with this work that really the engineers were captured by this. I mean, sort of the linear filter is sort of nowadays this work related to the linear filter is sort of mainstream in many engineering applications and outside engineering as well. So in the linear filter, we do away with the condition of stationarity for the signal. So the signal is no longer needed to be stationary. It is assumed to in continuous time is assumed to satisfy a linear equation. And I'm going to go through the details of this. It's just suffices to say that it covers such linear equations, such linear stochastic differential equations cover a lot of models that are out there. So, and this was great. Of course, your satellite, is just going in one direction. It's difficult to think of a model for the satellite as being a stationary signal. So, but this is possible, and it's possible to use this model for a satellite or indeed many other applications. And the observation is assumed to be again linear. So what you have in here, you have, this is the sensor function. This is the same function h. So the sensor function is linear in the signal, and we have some coefficients here, or alpha in the signal, and you add noise to it. So really the idea is that the linear filter you have to have a linear stochastic differential equation for the signal, you have to have a linear sensor function, and you have to assume that the initial condition for the signal is normal. So this only works under these constraints, and the theorem that is attributed to Busey and Kalman, and I put here 1961, and I'll come back to this, says that that distribution, that block that I showed you on my illustration, is really a normal distribution with some mean and some covariance matrix. And what I wrote in here, I wrote the evolution. I wrote everything in sort of dimension 1, but this is valid in any dimension. So the mean is random, right? So that's the equation, the evolution equation for the mean of this distribution. It's driven by y. That's why it's random. It's driven by y. If you can fix the trajectory of y, sort of, this is deterministic, and then the variance in dimensional covariance in higher dimension is deterministic. And this is great news because you can compute this beforehand, before beginning the whole process of estimation, and then you can just store this and use it to use R into the equation for the mean to compute the mean. So that's a very good thing, and it was exploited in the 60s when this was applied to all the flights or the space missions to the moon. You know, at the time, the calculators were not very powerful, and so the only thing they could do was to make sure that this is the system was, for example, 6-dimensional. You had 3 dimensions for the position of the satellite and 3 dimensions for the velocity of the satellite, and you had to solve this online. You have to use your calculator, your computers to solve this online, a 6-dimensional system online, and you didn't have to you didn't have to compute this online. You just store this and use it. So that was the thing that was very useful at the time. Nowadays, you can solve stochastic differential equations with dimension, 1,000 easily. But this was very helpful. So this was done, and so what is the history behind this? So the history is, so first of all, this was applied, as I said, by NASA to get for all these missions, the Apollo missions and Mariner missions and so on. And the reason was that Bussy was working for NASA. So Bussy was the driving force at NASA, and he's done some work. He's done a lot of work for NASA, but it was all classified. You know, the Cold War was raging there at the time, and he wasn't publishing anything. And on the other hand, Bussy was British Hungarian, who was publishing everywhere he could. So Bussy wanted a recognition for this, and he wrote a paper. He wrote a book in '87 where he explained how filtering was used by NASA to get all these Apollo missions to the moon. And in the book, there's this paragraph where he actually explains that he's done this work, a lot of work on the discrete version of the linear filtering in the periods 57, 59, and independently of Kalman, published in sort of internal reports, and then they started to talk to each other in 1960, and then they published this paper in 1961, which is really the paper containing the result I've just shown. So there isn't, they worked independently for a few years, and then they came together and they published this paper. What's interesting is that the paper is always quoted as Kalman and Bussy. In mathematics, you would expect to have the alphabetical order to call it the Bussy and Kalman. I don't know why it's that. If people know this, it would be nice to know. But unfortunately, somehow, this sort of may hint that Kalman had a bigger impact or influence on the paper, which is probably not true. And unfortunately, as a result of this, a lot of this work is attributed mostly to Kalman and not to Bussy.
So was any of this classified in the beginning?
Yes, so Bussy's work was classified. This work in the 57 to 59 was classified. It wasn't public. It wasn't public knowledge. As a result of the fact that sort of a lot of people attributed this work to Kalman, it became known as the Kalman-Bussy filter, not the Bussy-Kalman filter. And then later on, when people started to try to extend this work beyond the linear Gaussian framework, any extension was called an extended Kalman filter. So Bussy was forgotten altogether, which is very unfortunate. But anyway, so people, the linear Kalman filter enjoyed an amazing success, and people started to try to extend this work to nonlinear case, to the nonlinear case, or to a case where the initial condition is not Gaussian. So if you lose either one of these two conditions, nothing works. I mean, the linear filter doesn't work. So you try to do something. If you take a nonlinear system, which this is an example of nonlinear system, what you could do, you could say, well, okay, so I'm going to still approximate this nonlinear system with something with a normal distribution, with some mean and some covariance metrics, and sort of by extension, one can deduce the evolution for the conditional mean and the evolution for the covariance metrics. So if you do that, that's fine. There's no mathematics behind it. I mean, there's no theorem which says you're going to be very close to what you have. In fact, it turns out that in many cases you never have. I mean, your posterior distribution is not normal. It's not even unimodal. So you can have bimodal posterior distributions. But having said that, the extended Kalman filter enjoys an amazing popularity even nowadays. It's very simple to implement, and the engineering community and the computer science community have developed a lot of ways to cope with multimodality and many other problems that can appear. So it's still perhaps one of the most popular methods out there to approximate the conditional distribution of the signal. So that was the extended Kalman filter. And separately from this, people started to think about getting sort of rigorously the evolution equation for the nonlinear filter. So what happens when you have a signal which satisfies a general stochastic differential equation and an observation which satisfies an evolution equation like this, where the sensor function is some nonlinear function in there. And so the first to sort of begin to look into this, I say the first, but I'll come back to this and sort of quantify that, was Stratonovich. And those of you that know more about stochastic calculus, you will realize that this guy is there's a so-called Stratonovich integral, which is sort of a new method of stochastic integration. And so the Stratonovich integral was introduced by Stratonovich exactly to cope with this. So this is an example of theoretical development that happened as a result of a need to try to solve this problem in general. So he published, but so he presented the result in a very weird workshop on statistical radiophysics in Gorky, and he published. The first publication is again sort of a strange journal, and then he came back and he published in one of the more established mathematical journals at the time. And so when he published this thing, the reviews were not great. The editor himself, on the bottom of the first page of the paper says, "We are not sure about the validity of the arguments in this paper, but because of its importance, we decided to publish it anyway." That will not happen today. It will probably be rejected. It was so bad that there was a review that so mathematical reviews. I'm sure everybody knows about this. Reviews all the papers, and one of the major mathematicians at the time really said, I'm inclined to agree with what the editor says in there. And the big problem was that everybody was working, was using a stochastic calculus, the stochastic calculus developed by Ito, and Stratonovich was not using that. He was using a different stochastic calculus, which nobody knew about it until he got down and sort of wrote a whole book on the subject, and he explained exactly how stochastic calculus in his way, in the Stratonovich way, is developed. So the mathematical community in Soviet Union at the time was dead against him, and I myself have been told off because I keep calling the equation for the nonlinear filter the Kushner-Stratonovich equation. I was told I should not use Stratonovich, the name Stratonovich at all. So even after sort of 50 years, 10% people are still of the opinion that it should not be mentioned at all. What is more, in this book, which was published in '68, he says that if you look at this paper, which appeared in '59, and this is a major journal in the Soviet Union, he did the linear filtering equation. So he published the linear filtering equation prior to the work of Kalman and Bussy, and yet he was ignored. And yet today we call the linear filter the Kalman-Bussy filter. Well, anyway, so that was his work.
Was that in English or Russian?
No, it was in Russian. But Kalman should have been. I mean, I'm sure in the Eastern Bloc, Kalman should have known about this.
So after the book came out, because that was 8 years after he.
Yeah. So by then the Kalman. The Kalman was dominant. The Kalman was going everywhere and was saying that I've done all of this. You should just credit me and nobody else. And Simon can tell you a lot more about this. There was a meeting organized a few years back where Simon invited Kalman, and he can perhaps tell you one or two stories about him. Okay, so this was Shatonovich. On the other side of the Atlantic, Kushner did work on the nonlinear filter, and he applied the right stochastic calculus. He applied it to calculus. Kushner was an engineer, so he was careful. He developed perhaps not so rigorous the analysis in '64, quite a few years after Kalman, after Shatonovich, but the rigorous analysis was done in '67. And so, so that was it. And so the theorem. So this is a theorem which, as I said, I'm putting here Kushner and Shatonovich, but I will be told off, and I will keep being told off about that. So this gives you the evolution of pi t. And I know that if you're used. So what you do here, you say pi t is a probability measure. So to get the evolution equation, you take a test function phi. You integrate phi with respect to this probability measure. And that's the evolution equation for that. I know it looks very ugly, and for a talk, for an hour talk, it's difficult. I won't be able to say more. But all I will say is that it's a nonlinear equation. There's a first term in here where a here is a second order differential operator, and there's a nonlinear term in here which is driven by the observation process here. So it's essentially it's a PD written in week 4. You take a test function, you integrate the solution of the PD with it, and then you write this. So it comes very close to the notion of a generalized solution of a PD. It turns out that there's another titan that worked on this, and at the time Shiryaev basically worked on a generalization of the work that Shatonovich and Kushner did. So Shatonovich and Kushner said the measurement noise is independent of the signal, which is quite natural. Which is quite natural in engineering application. It's not so natural in financial applications. So Shiryaev gave the first derivation in the general case where the signal and the observation noise are correlated, and this was published in '66. The problem with that was this was a correct. The equations were correct, but he was assuming that this equation had a solution which had a density with respect to the Lebesgue measure, and that density was smooth, and that is actually very hard to justify. And I'm going to come back to that part in a few minutes. Basically, what ended the whole story was this two of people, Fujisaki, Kalyanpur, and Kunita, based on the work of Kailath in '68. We introduced something called an innovation process. These three people came along and really produced a standalone, complete and rigorous mathematical proof for the filtering equation. So from the '72 onwards, basically the equation satisfied by the nonlinear filter was known and was clear, it was rigorously proved. So these are 4 of the people that worked on this problem. There is a connection between that very ugly equation and another equation which is a lot simpler, and the connection is through this formula, which is sort of a more advanced form, an equivalent of the base formula, which was introduced by Kalyanpur and Schieber. So this is Kalyanpur and this is Schieber. They worked together on 4 papers. They did together 4 papers. Kalyanpur did a lot more papers. Interesting, Schieber only did these 4 papers with Kalyanpur, and that was it. And I was talking to Martin Clark, another one of the greats in the subject, and he met Schieber, and she said this was the most difficult work of her entire life. And she was very happy that she did this, but she didn't want to do more work in this area at all. Anyway, so based on these 2 papers, they came out with this formula here, which really is this representation of that conditional distribution in terms of a ratio between another measure, not a probability measure, divided by its total mass. Now, what's the point? What was the point of this equation? Well, the point of this equation is that this measure, which is no longer a probability distribution, but is just a measure, satisfies a much simpler equation, satisfies the linear equation. And that's the linear equation that is satisfied. So you really see here that it only has 2 terms. One of the terms can be found in the original equation as well. So this is a deterministic term. This A here is the infinitesimal generator of the signal. And the effect of this is an effect of the fact that the signal moves around in space. And then you have a linear term, a multiplicative term, which is an effect of the accumulation of data. So these are the 2 effects that that are involved in the evolution of this measurement process. And to get to pi t, all you have to do is to find out what the total mass of this measure is, and divide this equation by the total mass, and then you get pi t. So it's a lot easier to understand this equation when compared to the original one. And on this equation, it's sort of universally recognized that these 3 people worked on this equation: Duncan, Mortensen, and Sakai. Sakai probably did most work on this equation to the more general format. So it's usually called the Duncan, Mortensen, Sakai equation, but a lot of time it's just called the Sakai equation. So that's the equation for this is the equation for the linear version of pi t. And I mentioned earlier that the Shiraev deduced the equation for kind of the density of pi t. And it wasn't until the work of Pardue, Krylov, and Rozovsky in the 70s where really they proved that pi t has a density, and the density is sufficiently smooth to talk about a classical solution of the stochastic PDE satisfied by pi t. So really, they came in the 70s and they made it rigorous, the fact that pi t has a density, and they presented condition under which you have a density with respect to the bed measure, a condition under which you have the density is smooth. You can differentiate the density. And so the approach was different. Krylov and Rozovsky really were coming out from the classical PDE theorems, and they applied Sobolev inequalities and so on. Pardue was sort of much more functional analysis. So they really have different approach to the same problem. And we come to England, the last. A problem that sort of was discussed in the late 70s and early 80s was the fact that this pi t was a function of the observation. But what sort of function of the observation is pi t? And it turns out that there is a rigorous way to show that this is a continuous function of the observation. And that's really a very important property of pi t. And so this pi t has a representation called the robust representation, or you can think of pi t as a pathway representation of pi t in terms of the observation trajectory. And this is really very important from applied from numerical purposes, but also important theoretically, as this was one of the things that led Terry Lyons to develop the concept of graph path theory. So this is Martin Clark, who is still working at Imperial College, and this is Mark Davis, who both of them retired, but they are very active in various other areas. So I've just introduced here, wrote here, put here 3 papers, 3 of their papers. Mark Davis wrote a lot of papers in this area with collaborators. Some other people wrote papers in this area. Clark wrote just the one with no proof whatsoever. And about 6 years ago, I went to him and said, well, what is the proof of this? He said, actually, I don't have one. So I stepped in and I said, okay, let's write the proof. We wrote the proof to justify what he said in 1978. And we also generalized to some other people this to a much more general setup. Okay, so you have those equations, but actually, in the linear case, the great thing about the linear case was that you had an explicit description of pi t. It was a normal with some mean and some variance. The equations do not have an explicit solution. So people started to say, well, can we sort of, now that we have the equation, can we find some cases where there is an explicit solution? And along came Benesch, who said, yes, here is one. So he wrote a case where you have a nonlinear situation where f has to satisfy a certain constraint called the Benesch condition, and if that's the case, and if h is linear, then you can write explicitly the pi t. It's a bit uglier than the linear filter, but it's there. So this was great. This was in 1980s, so once he succeeded, people said, okay, perhaps there are some other equations out there. Let's try and find them. And a lot of PhD students started to work on this. On one hand, to try to find out the explicit solution. On one hand, to try to find out conditions under which explicit solutions exist. And it turned out that this is very difficult. It led to an expansion in the algebras. So there was a lot of connection in the algebras there, some success was there was some success done by Benesch, by Daum, and a lot of other people, but eventually it turned out that this was a dead end. It turned out that if you were to use something called Marevan calculus, you can prove that the filtering problem is essentially infinite dimensional. You shouldn't expect a solution in closed form. And this guy, Dan O'Con, used the Lie algebra equivalent interpretation of finite dimensional computable filter to show that basically they don't exist in general. So this was a bit disheartening. People were very upset, but basically there isn't a theorem there to say you can't find other solutions. Every once in a while there is a solution, there is another explicit solution coming out, but the general consensus is that basically finite dimensional solutions are the exception and not the rules. Coming back to Benesch worked for many years on this, and he did come up with a lot of solutions. Benesch's wife was the niece of Wiener, so that's an interesting connection there, and it'll be interesting to see what was the discussion of dinner time between Benesch, his niece, and Wiener. Anyway, so there's been a parallel development where basically the measurement noise is considered to be there's a different interpretation of probability theory where you assume that all the probabilities and all the measures encountered are not countably additive, but just finitely additive. So we can, you may or may not dispute this, but these two people, Karen Puller and Karen Dikar, really studied this very hard, and they developed not just the whole probabilistic construct, the whole stochastic calculus construct, but also everything that was out there in this area from this new, by assuming this new new axiom that any measure is finally additive. So they've done a lot of work on this, and again, there wasn't continuous union this. This is one of those things that remain in history as a side area. Okay, so I don't have much time left. So as I said, modern development. There's a lot of modern development, but I'm gonna keep it short. Basically, there's been a lot of work on the stability of the solution, the uniqueness of the solution, of the filtering problem, representation, Feynman-Case representation of the solutions, relevant calculus applied to the analysis of the solution of the filtering problem, connections between filtering and information theory, and there's been some work on the analysis of the extended Kalman filter. And so I've included here some of the contributors. I'm not going to go into this. So just a few facts about numerical methods. Obviously, there's a parallel history of numerical methods. So I've talked a lot about the extended Kalman filter, but this is not the only type of method employed there for computing, for approximating pi. There are other methods. I've enumerated the extended Kalman filter here. There are other methods, some based on the Benesch filter. There are moment methods where you say, okay, I'm going to assume that pi t can be approximated to with a probability measure whose density looks like this, and then I want to compute all the a's in some rigorous way. So so that's another method. There's spectral methods where what you do, you take pi t and you expand it in terms of the iterated integrals of the observation path, and then you try to say something about the coefficients in front. And there's PDE methods. So really here, I rewrite the equation now. This is now a function of space. So so this is a strong version of the equation. It looks like this. This A star here is the adjoint of the this second order differential operator that appeared in the weak form of the PDE, and then here you have the stochastic term, which has the solution multiplied by another function, by the sensor function, and you integrate with respect to the observation. So that's the strong version of the PDE. And of course, once you see the PDE, you say, well, okay, let's try and solve this numerically. And there are lots of methods. Every method that you have in the classical PDE analysis can be translated and applied to this. And you have wavelets methods, finite element methods, and so on. And the one that the sort of, in some sense, the entire program on Monte Carlo methods is devoted to falls into this area. So these are sort of particle filters or sequential Monte Carlo methods. So the idea here is that you want to approximate that blob, that pi t by a linear combination of Dirac measures. So you think of random particles that sort of sit there in the support of pi t. They carry some weight, and you want to find a way how to best approximate these random particles. Which, in order to find out where the particles, you put the particles, you can use the Monte Carlo method. So a lot of work has gone into this, and in my opinion, this is sort of the most successful class of methods, and I see a lot of future into this. And so to conclude, I will just like to show you some pictures of the people that contributed to numerical methods. Some of them were participants of our workshop. So we have Arnold Doucet here and Andrew Stewart, Pierre de Moran, Damien Obrigo, who came up with the projection methodology, Istvan Gyöngy from University of Edinburgh, who work a lot on sort of PDE methods for solving the strong version of the Zakai equation. François Legrand, who worked on the same topic, and Michael Tretiakov. I just want to bring to you one more thing. So this is David Main. He actually is one of the precursor of particle filters, of sequential Monte Carlo methods. He published his paper in 1968, where he said in 68 that you can try and approximate pi t using sort of random samples and sort of using a computer. Nobody cared about that. Computers were virtually in existence in 68, and everybody forgot about this. and the method was reinvented in 1991, I believe. Okay, so some more things, a lot of work has continued in this area. This is what's been done nowadays and much more. And I just want to conclude with sort of trying to show you basically what this area is in comparison, in connection with other areas. So I mentioned that there are these sister areas there which are either sort of synonymous or sort of very closely related, but stochastic filtering has influenced many other areas of mathematics. Of course, the continuous version has influenced many areas of stochastic analysis. It is a part of stochastic analysis. Stochastic PDEs were essentially developed as a need to make the filtering equation rigorous. There's been a lot of work in stochastic geometry because of that, and I omitted to say that there wasn't time. Rafa theory was developed having in mind stochastic filtering. Variable calculus, again, was influenced by stochastic filtering, and other subjects such as information theory, the algebras, and numerical analysis were influenced by the needs and the demands of this area. So I'm going to stop here and thank you very much for your attention.
So where's your photo?
Sorry?
Why isn't your photo on that previous page?
I am, okay, so I didn't want to put anything of my work in that, and I consider myself, young, the new generation. Yeah.
Can you make the slides available? I think that's a
Yeah,
that's a fantastic.
certainly. I mean, they'll be available anyway because the Newton Institute does this automatically.
Oh.
So was there, with Stojanovic's early paper, was there a theoretical hole that he patched up later on, or did he already have the Stojanovich calculus in
No,
place?
he didn't. He simply, so initially this was just a sort of non-rigorous formal derivation of the equations. And to make things work, he actually makes a mistake in the paper. So on top of the fact that he was not using the right stochastic calculus, he makes a mistake in the paper. But things were not rigorous. You have to imagine that in the 50s, people were still coming to terms with this new notion of stochastic calculus. It was, there were conferences where, somebody was coming in front of the audience and trying to tell everybody what stochastic calculus is. The work of Vito came in after the war, sort of, immediately after the war. So people were still trying to understand stochastic calculus, and these people were engineers. It was the engineers that basically sort of started the whole mathematical derivation of stochastic filtering. So no, there wasn't anything rigorous. The first complete and rigorous proof was done by the Chio. It's difficult to it's difficult to pinpoint exactly, but I say that the first self-contained proof was in here. That's why if you go to North Carolina, this is called the FKK equation. So we had a meeting a few years back, and there, so they call it the FKK equation because Kalyanpur worked for many years at a chapel here in North Carolina. So obviously everybody around him called it the FKK equation.
So there's
Yeah.
oh, sorry,
Yeah.
go ahead.
No, I was curious about the particle methods that you mentioned.
Yeah.
Is it known, error estimates or things like that in particular cases?
Everything is known. so you can ask everybody from our program. For the discrete time, there's been the French school has developed an immense body of knowledge. You can look at errors. You can look at sort of L2 errors. You can look at central limit theorems. You can look at large deviation, median deviations. Anything, any type of analysis has been done. So yes, the answer is yes. In continuous time, there's a lot less work. I've done work in continuous time, but again,
I was thinking in terms of the one of the last slides, would you have the stochastic PDE and then the kind of particle method?
Yeah.
There.
Yeah. So we can talk about that, and I can show you. There's rigorous analysis done by a number of people. So yeah, errors are there.
But one of these characters, you can probably guess which one, told me that Wiener died on a train to Stockholm trying to convince the Nobel Prize Committee to award him the Nobel Prize. Have you heard this
I do
rumor?
not know that. That's news to me, and I think I guess which one it is. Which character?
Or whether it's true or not.
No, I don't know. I mean, I think there's been 4 or 5 books on Wiener's autobiography.
Mhm.
I think I've read 3 of them, but I don't. I mean, in none of them there's
Doesn't
this
make
mention. No,
sense.
no. So,
Where was Sybil from? The woman?
sorry.
Where was Sybil? Was it Sybil, the woman?
So
Was she a civil servant?
I think she's in the States. I think it's Minnesota. I'm not 100% sure. So she retired. I think she retired in the 80s. Unfortunately, I found an obituary. There isn't a lot of information about her, but I found an obituary about her that simply said she dedicated her life to stochastic PDEs and worked very hard and was an esteemed member of the faculty. And after retirement, she took on sailing. That's all I can tell you. In addition to the 4 papers, except that Martin Carr told me that she said that the work with Kalimpur was the hardest work that she's ever done. They wrote 4 papers on this. Okay, so once again, thank you. And I want to just mention one other thing. So tomorrow, Antonietta Mira is going to give a talk at 2 o'clock. If you cannot make that talk, we booked this room literally from now till 4:30, and she is happy to talk to people that cannot make it tomorrow. So again, tomorrow is